Thank you, guys. Creative, right? You didn't see that coming. Solve a system of equations. Fun, right? Instead of x and y, I might have used the variables mu and sigma, but whatever. It's all good. Did you get the answers that Ryan got? Cool, right? All right. So, good. All based just on what we mean by a z-score, right? You can get that information. Right. We're going to hold the questions on homework for now, just because I think I'll be able to answer any two that we have. I think people did okay, though, it seems like. Before I launch into today's examples, I have a couple examples to show you today. I'd like to take a look at yesterday's PowerPoint and just say one or two things about that. Maybe let's not, or maybe you could do it quickly, I don't know. There was one problem like this on the homework, too, that asked you to compare this. I skipped over this yesterday. What do you think? How would you do this? Does this make sense? We've got 3 tests. It seems like, someone might be like, oh, I scored a 255 on the one test. That must be the one I did the best on, right? So, of course, we need to kind of understand how you did relative to other people on the test, right, based on how they're distributed. So, I don't know, the one in the homework was SAT, ACT, or whatever, right? Scoring well on this test, in this example, from our class notes yesterday, is maybe not that good, right? This is a test for neuroticism, okay? So we maybe want to score, low, but still, the question asks, what is the highest relative score based on these numbers? We don't have to calculate like p-value, we don't have to know what percentile you're in to know, we just have to know what the z-score is, right? So did you calculate the z-score for each of these? What do you think? Maybe you could go by feel first. What do you think? Actually compute these z-scores here. I'll do it too.
Oh, yeah.
You haven't already.
I thought this was the one.
This is not the one from the homework. The one from this is the test for neuroticism. This is though in your class notes from yesterday. We just skipped it. I thought we'd return to it and say something about it real quick. Because I think it's interesting. It's like a good use of z-scores to. So I'm getting a z-score of negative 1.17 approximately for that one. So somewhere else. Which one did we do? Score the highest on. Getting some. I mean, really, negative z-scores are like a good thing. On this one, aren't they? I'd like to have a negative z-score on this test. All right. So these are the 3 z-scores I'm getting. So which test did we do best on? Did we score the highest on? Yeah, A is the one we scored the highest on. I think this is the one we want maybe as our score though, right? So yeah, I'll try to avoid using the word best. I think we scored the best on the last one. But okay. Any other thoughts about that? That's like the one in the homework. So I just thought I'd highlight that. And then we this is where we ended yesterday, and I didn't get to say as much as I would have liked to. I think these are not that interesting. Maybe, we talked about this whole 1,000 or using negative 1,000 for positive and for negative infinity. I don't think they're any quite as interesting as this on your homework. But everyone turn your attention to this one right here now, if you will, and talk to me about how you would do that. How would you do that? I don't know. There are a couple good answers for how you might do that. What do you think? Yeah, right. And in fact, you could quicken your work a little bit by just saying because of the symmetry of the curve, it would just be twice the thing you first said, right? Probably z greater than 1.32. And actually, before we even begin, and maybe on all of these, I actually said it up here. I actually said this up here, but we were going quick at the end of the class issue, so we kind of ignored this. But on this one especially, let's be clear. What is it that we shade the area here? What area are we actually computing here? Well, just to be clear, by absolute value of z greater than 1.32, we mean this area. It's clear that Lisa knows that, but is everyone clear on that? Talking about those 1.32 and up and negative 1.32 and below. So you can compute it this way. Does anyone have another creative, interesting way to compute it? Given the picture too, maybe that helps you come up with another way. But I like your way. It's good. Nice exact way. another way that occurred to me is what Mona's going to say. Ready, Mona? Go. Yeah, 1 minus the section in the middle. You remember you can always use that to your advantage too. The fact that this curve has area 1 underneath of it. So either one of those, I don't know what the answer comes out to, you can figure it out, but either one of those would be a good way to compute it. You should get the same answer either way. Okay. Anything else you want to say about that? Okay, so yeah, I did say shade these, and I don't think the homework required you to do that, but I would like you to be able to draw these. You know, it doesn't have to be a perfect normal curve, but okay, so just, is that okay with everybody? All right, I think that's a reasonable expectation. I didn't dock you on the homework if you didn't do that. But. All right, and then the thing I didn't say, but I said, hey, check the notes, it's not hard, it's just type in the calculator command, is how to do these where we give you a p-value and I'd like you to come up with a z-score. For these especially, I think it's helpful to shade because, I don't know, for some reason going forward is easier, right? So for instance, on this first one here, what are we actually doing? We're looking for the z-score for which the probability that some z-score you bring to me is less than this value is 63%. So if you were to draw this z-score on here somewhere, this z0, where would it go? Z0. Z0 is the score that has 63% of values below it. So where does it live? Is it positive or negative? It's got to be over here somewhere, right? Yeah, it's positive. It's got 63% of the curve below it, right? Right, this is our p-value. 0.63 lives below it, yeah. So, is that clear? So z0 is equal to, well, and this is where the calculator command comes in, okay? So type into your calculator, inv norm, this is on the same menu as normal CDF, and then 0.63. This is convenient first example because inverse normal always interprets your command to mean the p-value to the left of the value you're interested in finding, right? So it always uses left tail probabilities just because there's no good reason necessarily for it to do that. It's just if it's convention. So whatever this comes out to be, let me do it too. I don't have it. .332. Yay. Okay. So that is. Does it make sense? So we're saying that's the 63rd percentile. .332. That z-score. Okay. Great. How about this one? Let's do all 4 of these just for fun. Anyone have it? Get my calculator. What'd you get? Oh, you didn't actually have to use your calculator? Oh, okay. Why is that maybe, if it's not immediately obvious to others, what did I just do with my calculator? Started some app, okay, whatever. Tell me why that, if it's not immediately obvious to other people, explain then, what's going on? Why is it the same answer? How do you see that? In fact, it's the same picture, right? Except we're talking about this area right here, right? Which is 0.37. Right, so hopefully that's clear from the picture. Good. What about this one? All right, let me break out my. Okay, wait, hold up. What's the answer? 0. Oh, okay. Okay, 0. I didn't have to use my calculator for that one either? Okay. How about this last one? Yeah, it's negative 0.332. And you didn't have to use your calculator for that either? Okay, I just want to make sure I'm giving you these particular problems to emphasize, like, I hope you know more about this curve than you think you do, right? You've got the symmetry, you've got the complement, the fact that the area underneath of it is 1. Which helps you out. Yeah, before you even come to this problem, you should kind of have an idea of what this should be. All right, we're looking for the value that has an area above it of 0.63. Now, the one mistake that everyone would make here, that I want to caution you against, is thinking the following. Oh, I did this problem before. I remember up here. I did this problem before. It's 0.332. But no, excuse me, it's not 0.332. It's 1 minus 0.332 because of the other. 1 minus 0.332. No, it's not, right? Careful what you're working with. It's easy to confuse, especially with a z-score like this. I intentionally set these problems up so this would be confusing, okay? It just kind of looks like a p-value, right? Let's just be clear. It's not. It's not a p-value, right? This could be 1.332, right? We could get an answer like that. Okay. Can it be negative? Yeah, of course it can. This is not a p-value. Let's just be clear in our minds, because some people will be like, oh, I need to do 1 minus this z-score. There's never a time when you will do 1 minus a z-score, please. Okay. So drawing the picture, I think, adds clarity to the process too. Make sure you actually understand what you're coming to the curve with and what you want from the curve, and draw a little picture to convince yourself of this kind of symmetry arguments we've just been making. All right. So maybe I'm preaching to the choir. You all figured that out last night probably as you were doing the homework. So whatever. I just didn't finish what I wanted to say yesterday. You know. So you taught yourself, I'm sure. All right, here we go. Let's say something about applications of normal distribution. It's pretty cute. The things we've been doing right now, nice kind of clinical environment. P's and Z's and stuff. But what happens when I give you like a problem with words in it? Oh, man. It's not bad though, right? It's easy. It's going to take no time at all. As usual, staff people you can use. You know. You can just stay quiet, I think. I mean, if you have some constructive thing to add or some mistake I'm making, please, by all means, speak up. So, I think you'll get the idea pretty quickly after doing just one example, maybe. But, see, look, do you see all the words? So, someone read for us. We need a reader, like someone like. Who likes to read? Who likes to read? Taylor, you want to read the first one for us? You don't want to read it? No. That just got shut down. So you want to take it?
In tests conducted on jet pilots, it has been found that blackout thresholds are normally distributed with a mean of 4.7 G. Is that it? Okay, 4.7 Gs, and a standard deviation of 0.8 Gs. Found the probability of randomly selecting a jet pilot with a blackout threshold that is less than 3.5 Gs.
All right. Yeah. What's a G, by the way? This is not really. It's immaterial, actually. We're just answering this question. But, yeah. So it's. What do you think? Would you black out at 4.7 Gs?
If you were to, I can just squeeze the bottom in on the right.
You might. I don't know. It's the average blackout for jet pilots. So. So I would guess that. I mean, that's a lot. It's more than you think, right? You're used to 1 G all the time, but even 2 Gs is a lot.
Just waistbands that like basically cuts off your circulation on the legs, so it keeps your blood flowing.
Okay, so they have some strategies for avoiding blackout, maybe. I don't know.
You see the thing at Disney World, like where like you go into the mall and you issue this, like it goes more than 2 Gs or something.
And it goes more than 2 Gs?
I think it's like a very low.
It makes you, yeah. I would guess that like your regular roller coaster ride at an amusement park don't ever even approach anything close to this, right? Like, right? So this is for jet pilots. You know, having a jet pilot pass out is like not a good thing. So this is a good thing to study. Okay, so there are 2 pictures we can draw here. We're interested in 3.5 Gs. By the way, there's 3.5. If you were to like think z-scores here, like does 3.5 Gs, does that have a positive or negative z-score on here? What is it? It's got a negative z-score. Okay. There are 2 pictures I'm going to draw. In reality, if you're drawing things, you can just draw one if you like. But I'm going to draw them both just to illustrate the picture here on the first one. We can go a little quicker on other examples. But this is the distribution we're looking at. It's a normal distribution centered at 4.7 Gs. And we're interested in particular about this value down here, x equals 3.5 Gs, and values below that, right? So we're asking, what is this area? Right? Is it the question in our minds clear? We got this normal distribution centered at 4.7. We're marking 3.5, shading below, and asking what's that area, right? So written out, we're asking what is the probability that x, which is our we'll call x our random variable, okay? What is the probability that a random variable x takes on values less than 3.5, right? That is the question, okay? There is another picture, though. Now I'm going to draw another normal distribution. This is the standard normal distribution this time, with mean 0, right, and standard deviation 1. What z-score are we talking about here? Because I'm going to ask the same question here. It's the same question, in fact, right? The answer to this question is the same as the answer to this question down here. What is the z-score associated with 3.5? Yeah, did anyone compute it yet? 3.5 minus 4.7 all over 0.8. Negative 1.5, do you guys agree with David? Okay. Good. So this, we've just actually, even though this seems pretty basic, we've really just computed, we've actually done like a transformation of random variables. This is what we've actually just done. I know that sounds really awesome, doesn't it? That's what we just did. We did a transformation of random variables. We've got a random variable asking the probability, what is the probability that our random variable x is less than 3.5 is equivalent to asking what is the probability that our random variable z is less than negative 1.5. Okay, so this now has turned this complicated word problem into just something we did last night, right? So this is exactly, in fact, the kind of thing you did last night, right? You can do normal CDF on your calculator, so someone race me to the answer here. Negative 1,000, negative 1.5, and you get an approximate value of, what did you say? 0.0? 0.0668. Okay, so about 6.7% chance that you're down there. You're someone who blacks out at 3.5 G's or less. Good. Don't tell your stat teachers, but you can also do this in one command without actually having to do any of this work down here, right? You can just type in normal CDF, negative 1,000, negative 1.5, and then 4.7, comma, 0.8. And in one command, that will give you this too. So try that too. Go ahead. Does it work? Did anyone try that? Right. So now does that mean you never have to calculate a z-score again? Why did we do all this stuff down here at the bottom of the page? If we can just type this in right away. I mean, you should use your calculator for its full resources. So feel free to do this. I'm fine with you doing this up top. Okay. That doesn't mean you can't forget z-scores, right? Like the one up today, or like there are plenty of questions that we can ask you, or we can just have to ask you straight up. Hey, what's the z-score? Go. You know, and you should be able to identify that. One caution I might give you on typing this in is what if, imagine if the mean of some distribution we're looking at is 520 and the standard deviation is 30 or something like that. Why would this maybe be a problem? Do you have to make one more little adjustment possibly? It may turn out that, you know, for standard normal distribution, negative 1,000 is basically negative infinity. But if your mean, like if the mean of your distribution is like 5,000, right, and your standard deviation is 500, right, then no more is this like negative infinity. So your rule of thumb, instead of just being like, oh, well, we just always use negative and positive 1,000 for negative and positive infinity, maybe you use like 1,000 times the precision of the data instead as your rule if you're going to do that. So just be careful, right? So maybe you still want to do the normal CDF with the mean in this way, calculating z-scores just to be safe. I don't know, whatever. You could try it, yeah.
For the like shortcut version, would it be 3.5 as like a number, or would it be?
I'm sorry. Yeah, 3.5. Sorry. Good catch. Yeah.
Would it be positive 3.5 or just?
Yeah, it's positive.
It's positive 3.5. Sorry, I was copying and pasting from down below here. Testing you. All right, now try entering that in your calculator and see if you get the same value. You should, of course, get the same value. Yeah. All right. Good work. 10 imaginary bonus points to Matthias for finding the error. Moving smartly along. Okay, here we go. I'm very interested in this question because I just had a little baby. Yeah, this one's about newborns. Thank you. Mona wants to read this one.
Assume the weights of newborn children are normally distributed with a mean of 116 ounces and standard deviation of 12 ounces. Find the probability of randomly selecting a newborn child whose weight is between A, 108 ounces and 174 ounces, and B, 110 ounces and 135 ounces.
So let's draw a picture, but I mean, really, the calculation is going to be like a one-liner. It's not a big deal here. It turns out, what is it, the mean? 116. So we're like right in the middle here. 108 to 124 is a nice symmetric area in the middle here. 8 below and 8 above. So we're looking for that area right there. And just to skip to the punch, right, maybe we won't even do B. We're looking for the probability that 108 is less than X is less than 124. And you can just get that again on your calculator, right? In fact, without even calculating z-scores. Let's just do it the fast way here this time. Normal CDF. 108 is the left endpoint. 124 is the right endpoint. 116 is the mean. 12 is the standard deviation. Type that in. Give me an approximate value. Call it a day. Yeah? And then you can do B too. In fact, I'm going to skip B because it's just the same problem. Okay. Is that okay? Feel free to calculate z-scores if you like, but I don't need you to do that if I don't ask. Okay? I might ask, but I didn't, so whatever. So I'm getting, and this looks reasonable based on my picture too, 0.495. Is that what you guys get to? Okay. Great. All right, there's one more. Let's see if we can say something about the last example before the bell rings here in a minute. At least let's set this up. Why is this a different problem? Maybe more interesting to us. We should say something about it. Everyone read it to yourself quickly. Yeah, this time we don't know the value, the score, right? With a mean of 500 and standard deviation at 70% of all examinees pass, right? We're asking, what is this value X, right? Given this picture, do you think you can go and do this problem? Okay, I would have liked to finish that one, but, you know, you got to leave some mystery in your lives, you know? All right. And your homework for tonight is also this label, but it's this worksheet right here. Word problem. I'm not saying
That I hope I could probably not go on this quarter because my grade is very poor. I am not certain.
have a great day, you guys.
That's nothing, absolutely nothing. We can turn this in.
Are you talking about chat again, Jerry?
We have states this weekend, so. Where?